Hello, my friend. Wherever you are and whatever kind of day you've had, I'm glad you're here. Tonight, we'll drift far beyond our familiar sky to visit strange star systems where the rules of light and gravity don't quite behave the way we expect. So close your eyes if you'd like. Let's begin this quiet journey through a universe of wonder. Chapter 1. Worlds with two suns, the binary dancers. It's easy to take for granted the image of a single sun rising and setting each day. One steady source of light, one gravitational anchor, one celestial rhythm to live by. But our solar system, with its lone star at the center, is far from typical. In fact, when astronomers began systematically studying star systems beyond our own, they found that single star systems like ours might actually be the exception, not the rule. Binary star systems, where two stars orbit around a common center of mass, are remarkably common. It's estimated that over half of all stars in the Milky Way are part of binary or multiple star systems. Some stars orbit each other at vast distances, while others spin in tight embraces, completing an orbit in mere days. And in many of these systems, there is something even more extraordinary: planets. Planets that somehow manage to hold on to a stable orbit despite the gravitational dance of two luminous giants. The kind of planetary arrangement we're focusing on here is known as an S-type orbit. In this configuration, a planet orbits one star in the binary pair, while the second star looms farther away in the sky. This is quite different from the Circumbinary setup, where a planet orbits around both stars together. In an S-type system, the primary star acts as the planet's main sun, providing most of its light and warmth, while the companion star may appear as a second, perhaps smaller or more distant sun, rising and setting like a secondary moon, or hovering low in the sky for weeks or months at a time, depending on the geometry. The dynamics of such systems are complex. For a planet to remain in a stable S-type orbit, it must be close enough to its host star that the gravitational influence of the companion star doesn't destabilize it. If the second star is too close, or if the planet's orbit is too wide, gravitational perturbations could nudge it into an elongated, eccentric orbit, or eject it entirely from the system. But if the orbital distances are just right, these planets can remain stable for billions of years. Astronomers have found real examples of these kinds of systems. One of the most iconic is Kepler 16b, sometimes called the real-life Tatooine, in homage to the fictional desert planet from Star Wars. But Kepler 16b isn't actually an S-type world, it's circumbinary. Still, its discovery ignited public imagination and pushed scientists to re-examine what kinds of planetary orbits were possible. True S-type planets are more difficult to confirm, but models suggest they could be common, especially in systems where the companion star is far away. Imagine standing on the surface of such a planet. Your main sun arcs through the sky much like ours, bathing the landscape in warmth and light. But somewhere else, perhaps on the horizon or overhead depending on the orbital phase, a second star may rise, dimmer or more radiant, perhaps a red dwarf or a brilliant white subgiant. On some days, both suns might grace the sky at once. On others, the secondary sun might not rise at all. The interplay of light could be subtle or dramatic, depending on the brightness and distance of each star. This second sun might be just a bright point, casting soft shadows alongside the sharper ones of the main sun. Or it could be bright enough to extend the length of daylight, eliminating night for days at a time. And when both stars dip below the horizon, the resulting darkness could be temporary, or oddly tinted by residual twilight. On some worlds, sunrise and sunset wouldn't be clean transitions, but elongated performances with one sun fading as the other begins to rise. Seasons on such a planet would be influenced by more than just axial tilt. If the companion star's gravitational tug causes subtle wobbles in the planet's orbit, long-term climate cycles might emerge. Some researchers have proposed that these Milankovitch-like cycles, caused by variations in orbital eccentricity and inclination, could be far more pronounced in multi-star systems. The result might be centuries-long shifts in temperature or atmospheric composition, global changes set in motion by stellar choreography. But would such a world be habitable? That depends on many factors. The first, of course, is whether the planet falls within the habitable zone of its primary star, the region where temperatures allow for liquid water to exist on the surface. If the secondary star is relatively dim or distant, it may not contribute much heat, though it could still affect light levels and atmospheric chemistry. If it's a powerful star, say a large hot B-type, it could subject the planet to intense radiation or destabilize its orbit entirely. Still, theoretical models and simulations show that habitable conditions are possible in S-type binary systems, provided the parameters are just right. A planet with a stable orbit, orbiting a quiet, long-lived star like a K-dwarf or M-dwarf, and with a secondary star far enough not to interfere, this could be a cradle for life, not unlike our own Earth. And perhaps even more interestingly, the presence of a second sun might create ecological niches we can't yet imagine. Organisms adapted to dual spectral inputs, or ecosystems shaped by alternating light regimes. The visual beauty of such worlds would be unlike anything we know. Shadows might fall in two directions. Sunsets could be layered, with one sun dipping below the horizon while another lingers in the sky, casting a different hue across the clouds. The sky might shift color not just with the time of day, but with the changing angles of the stars. And for civilizations that might evolve on such a world, the notion of a day would be more fluid, more poetic, a harmony of stellar cycles rather than a single solar rhythm. There's also something poetic about the idea that a planet could exist in such a fragile balance, caught between two immense bodies, orbiting one while the other looms. A constant gravitational whisper in the sky. And yet, it endures. The math works, the orbits hold. In the cold logic of Newtonian mechanics and general relativity, this is not chaos, but order. Not impossibility, but configuration. The universe, it seems, has many ways of allowing complexity to arise. In recent years, advances in exoplanet detection, particularly the transit method used by missions like Kepler and TESS, have allowed astronomers to peer into these systems with increasing detail. When a planet passes in front of its host star, the resulting dip in brightness can reveal not just the planet's size, but sometimes clues about its atmosphere, orbit, and interaction with nearby stars. Detecting planets in binary systems is more difficult than in single-star systems, but it's no longer considered exotic. In fact, it's becoming expected. And yet, we are still only scratching the surface. The vastness of our galaxy means there could be countless binary systems with stable Earth-like worlds orbiting one star and basking in the distant glow of another. Some may host oceans, others may be locked in icy slumber, some may be lifeless, but others, well, the possibility remains open. Beyond visual aesthetics and orbital mechanics, binary systems also influence planetary formation itself. In single-star systems like ours, planets coalesce from a protoplanetary disk, a vast swirling cloud of gas and dust that gradually clumps together over millions of years. In a binary system, this process becomes far more complex. The gravitational tug-of-war between two stars can disrupt the shape and density of the disk, carving out gaps or warping it into tilted or spiral patterns. These distortions can alter how and where planets form, sometimes speeding up formation in certain regions while halting it entirely in others. Yet surprisingly, this disruption doesn't always hinder planet formation. In some cases, it may encourage it by concentrating material in certain bands or pockets, seeding the emergence of planetary cores more efficiently. Numerical simulations suggest that planets in S-type orbits might still grow large and stable under the right conditions, especially when the stellar companion is distant or has a gentle orbital path. Observations of dusty disks around young binary systems confirm that protoplanetary structures can and do exist in these dynamic environments. Astronomers are also exploring how magnetic fields influence planetary evolution in binary systems. A secondary star, depending on its type and activity, might bathe the system in periodic bursts of ultraviolet or X-ray radiation. This additional radiation can affect a planet's atmosphere, potentially stripping lighter gases away over time or driving chemical reactions in the upper layers. In some scenarios, this could erode habitability. In others, it might catalyze the development of complex prebiotic chemistry. Much depends on the intensity, frequency, and wavelength of the radiation, as well as the planet's distance and atmospheric composition. The orbital dance between the two stars also evolves over time. Binary stars can lose angular momentum through stellar winds or magnetic braking, causing their orbits to shrink or change shape. Over millions or billions of years, this evolution could impact any planets orbiting nearby. A once safe S-type orbit could become unstable if the secondary star drifts closer. Alternatively, a chaotic system might calm down as the stars settle into a more distant circular configuration. In this way, a planet's long-term fate is tied not just to its own orbit, but to the evolving relationship between the stars that define its sky. And still, somewhere in all of this, in the shifting dust, in the invisible currents of gravity, in the soft arithmetic of light, a planet may quietly turn. Its skies may hold two suns, its seas may glow with doubled reflections, and maybe, just maybe, something will one day look up from its surface and wonder, as we do, why this place? Why this balance? What does it mean to exist in a world where day and night are written not by one sun but two? Chapter 2: Three-Star Sunsets, the Chaotic Beauty of Trinary Systems. The image of a setting sun is one of the most universally familiar moments in a planetary day. Its warmth, its gentle descent beyond the horizon, and the long shadows it casts are constants for life as we know it. But elsewhere in the cosmos, the skies do not always yield to just one sun, nor even two. In some regions of the galaxy, there are systems where three stars orbit each other in a complex, gravitationally interwoven performance. These trinary systems, far more common than once imagined, introduce a new kind of order, one that seems chaotic, but can persist for millions or even billions of years under the right conditions. Triple star systems, or trinary systems, are gravitationally bound arrangements of three stars interacting through mutual attraction and orbital momentum. They are not rare. Observational studies suggest that as many as 10% of all stellar systems in the Milky Way consist of three or more stars. These configurations can be hierarchical, with two stars tightly orbiting each other while a third orbits the pair at a greater distance. They can also form less stable and more dynamically intricate groupings, where each star plays a significant role in shaping the system's long-term behavior. For a planet orbiting within such a system, the experience of light, time, and motion becomes something entirely alien compared to the gentle clockwork of a solitary star. Depending on its placement, the planet may orbit one star while the other two remain distant companions. Or it may orbit around a close binary pair, with the third star influencing it subtly from afar. In rarer scenarios, some planets may be caught in even more complex loops, navigating a gravitational field that is never quite the same from one orbit to the next. These systems are fundamentally governed by Newtonian mechanics and the principles of gravitational dynamics. But when three or more masses are involved, the problem quickly becomes nonlinear and sensitive to initial conditions. This is known as the three-body problem, a cornerstone of chaos theory and celestial mechanics. While two-body systems follow predictable elliptical orbits, Three-body systems can produce unstable orbits, resonances, or even ejections of one of the stars over time. Despite this inherent complexity, nature often finds a path toward temporary or quasi-stable arrangements that can last for astronomical timescales. In most observed trinary systems with planets, stability emerges through a hierarchical architecture. The two closest stars orbit each other tightly, sometimes separated by only a few astronomical units or less. This pair acts as a single gravitational source from the planet's perspective. The third star, located much farther away, orbits the inner binary along a more extended, sometimes inclined trajectory. This arrangement allows a planet to either orbit one of the close stars in an S-type orbit, or circle both inner stars in a P-type circumbinary orbit, all while the distant third star exerts a more diffuse but persistent gravitational influence on the system. The light environment on such a planet would be nothing short of astonishing. The dominant star, or stars, would dictate the primary daylight cycle, but the additional sun could rise or set on a different schedule entirely. Some days might begin with a soft, cool glow from a distant red dwarf, followed by the piercing white light of a hotter main sequence companion. Other days might feature overlapping sunrises, casting multiple shadows at conflicting angles. The color of the sky could shift with the positions of the stars, turning golden under one sun and bluish under another, perhaps even tinged with violet or orange, as the stellar spectra blend together across the planet's atmosphere. Unlike binary systems where the gravitational dynamics are often more predictable, triple systems introduce significant variations in planetary climate potential. A planet's orbit may be perturbed on multiple timescales, not only by a close secondary star, but also by the long-period motion of the third. This could affect orbital eccentricity, axial tilt, and even rotational stability. Climate models suggest that in some configurations, a planet could experience extreme variations in temperature and insolation, leading to episodic ice ages, hyperthermal events, or wildly shifting seasonal patterns. In others, however, gravitational resonances and the damping effects of atmospheric inertia could stabilize the climate in unexpected ways. Long-term stability in trinary systems is also influenced by the mutual inclinations of the stars and the planet's orbital plane. If the third star's orbit is highly inclined relative to the inner binary and the planet's motion, it can trigger Kozai-Leydov cycles, oscillations in the planet's eccentricity and inclination that occur over thousands to millions of years. These can result in increased orbital elongation, sometimes pulling the planet dangerously close to its host star before pushing it back out again. In extreme cases, such oscillations could cause tidal heating, orbital disruption, or even planetary ejection. Yet, some systems appear to have found stable Kozai equilibria, where the chaotic forces balance out into enduring configurations. One of the most studied trinary systems with planets is HD 131399, located approximately 320 light-years away in the constellation Centaurus. It contains three stars, HD 131399A, B, and C, with at least one confirmed planet, HD 131399AB, orbiting the primary star. The dynamics of this system are complex, and its long-term stability is still under investigation. Simulations suggest that over tens of millions of years, the planet's orbit may become unstable, possibly resulting in ejection or capture by one of the companion stars. Still, its current configuration offers a valuable insight into the possible lives of planets in trinary systems and the razor-thin margins between balance and collapse. The process of planet formation in triple-star systems remains a major area of active research. Protoplanetary disks in these environments may be truncated, warped, or torqued by the shifting gravitational field of nearby stars. Such distortions can affect not only the distribution of material, but also the timescales of planet formation. In some scenarios, the relative motion of the stars may promote rapid growth of planetesimals in high-density zones. In others, turbulence and heat from close stellar encounters may prevent accretion entirely. Despite these challenges, it is increasingly clear that nature does not shy away from complexity. Planet candidates have now been detected in systems once thought too unstable to support them. Kepler-64, for example, is a quadruple star system, two pairs of stars orbiting each other, with a planet orbiting the inner binary. The planet must navigate the gravitational influence of at least 3 other stars, and yet it appears to do so successfully. This suggests that planets may be more resilient than once believed, capable of surviving, even thriving, in environments far stranger than anything our solar system presents. For an observer living on a planet in a trinary system, the passage of time would be marked by more than just a daily sunrise and sunset. The motions of the stars would introduce long-term cycles of brightness and shadow. Perhaps every few decades, the distant third star would move closer in the sky, brightening the night and altering the nocturnal climate. Perhaps eclipses would occur regularly as one star passed in front of another, briefly dimming the light. The concept of a year might become a complex function of multiple orbital periods, layered atop one another like musical harmonies. Civilizations, if they emerged in such systems, might develop calendars and mythologies built around the triple dance of their suns. Light and darkness would not be binary states, but a spectrum, from the blazing brilliance of 3 suns aligned to the eerie dimness of only one star in the sky. Cultural rhythms, agricultural patterns, and even psychological perceptions of time might evolve under the influence of this multi-dimensional celestial environment. As our detection capabilities improve, we are beginning to find more planets in trinary systems, each one forcing us to broaden our understanding of planetary dynamics. Ground-based instruments, especially those utilizing adaptive optics, will continue to resolve individual stars in these tangled systems, allowing astronomers to distinguish between false positives and real planetary companions. In the future, we may discover that many of the most stable planetary environments are not in isolation, but nestled within the quiet resonance of multiple suns. We may find that 3-star systems, far from being gravitational chaos, represent another valid configuration in the grand experiment of cosmic architecture. Not random, but ordered in a different key. Not dangerous, but simply unfamiliar. And in the silence between each sunrise, a thought might linger, that somewhere in the universe, there is a planet where sunsets come in 3s, each star casting a different shade, each light a memory of a different part of the cosmos, and that perhaps under those braided beams of light, something once looked up and dreamed. Chapter 3. Living near a quasar. What if your sun was a black hole? To imagine a star system ruled not by a shining ball of plasma, but by a gravitational chasm, a black hole, is to step far outside the comfortable blueprint of our solar system. Yet in the vast theater of the universe, such systems do exist, and in some of the most luminous and energetic forms known, quasars. These cosmic powerhouses are not stars in the traditional sense, but the blazing hearts of galaxies, supermassive black holes actively feeding on surrounding matter. Their brilliance is not born of fusion, but of infall, not radiated from a surface, but from a maelstrom of particles caught in an inescapable descent. Quasars, or quasi-stellar objects, were first identified in the 1960s as point-like sources of immense radio emissions. Their optical spectra revealed redshifts so large they could only be explained by distances spanning billions of light years. The power output implied by those distances was staggering. Many quasars outshine their host galaxies by factors of up to 1,000. And yet, the source of this luminosity is not a star, but matter falling into a black hole millions or even billions of times more massive than the sun. As matter spirals toward the event horizon of a supermassive black hole, it forms what's called an accretion disk. This disk can reach temperatures of millions of degrees Kelvin, emitting copious amounts of electromagnetic radiation across the spectrum, from X-rays to visible light to radio waves. Magnetic fields twist through the disk and channel some of the infalling material into jets that can shoot out thousands of light years into space, moving at nearly the speed of light. These jets are not decorative. They carry enormous amounts of energy, reshaping the interstellar medium of their galaxies and possibly even influencing galactic evolution. To speak of living near a quasar is to enter the realm of extreme astrophysics. Quasars are not gentle sources of light. They are radiation engines, their output capable of stripping atmospheres from planets, ionizing gas clouds over intergalactic distances, and creating radiation zones that would be utterly hostile to known life. Any planetary system within a few dozen light years of an active quasar's central engine would likely be uninhabitable, not because of gravitational disruption, but because of the continuous blast of high-energy radiation. Yet there are reasons to believe that planetary systems can exist in galaxies hosting quasars. After all, quasars are simply a phase in galactic evolution. Most large galaxies, including our own Milky Way, are thought to contain supermassive black holes at their centers. And many of these black holes go through active and quiet phases. A quasar is a galaxy caught in the act of feeding. It is not a permanent condition, but a transient one. A few 100 million years of intense activity, followed by eons of dormancy. Planets in the outer regions of these galaxies, thousands or tens of thousands of light years from the core, would be largely insulated from the quasar's most extreme effects. They might still receive elevated background radiation, or encounter occasional shock waves from relativistic jets sweeping across the galactic plane. But the severity of those effects would decrease with distance. In this sense, living in a galaxy with a quasar is not unlike living near a volcano. Safety is a matter of how far away you are and how active the center remains. But what if a planet found itself much closer? Could a planetary system orbiting a stellar mass black hole, or even a black hole within a less active galactic nucleus, support stable conditions? Interestingly, the answer may be yes. A black hole in itself does not actively destroy nearby matter unless that matter crosses the event horizon. From a distance, a black hole's gravitational field behaves just like that of any other object with the same mass. If our sun were replaced with a black hole of the same mass, the planets would continue to orbit as they do, albeit in total darkness. In fact, black holes in binary systems have been observed to maintain long-term stability. In X-ray binary systems, a stellar mass black hole is in close orbit with a companion star, drawing material from it through Roche lobe overflow. This accreting material forms a disk and emits X-rays as it spirals inward. While such systems are compact and extreme, they provide real-world laboratories for understanding how matter can stably orbit black holes, and how complex structures can persist even in regions where gravity is overwhelming. Theoretical work has explored the possibility of habitable zones near quiescent black holes. If a black hole were not actively feeding, if it lacked an accretion disk or relativistic jets, it would be invisible against the backdrop of space, but gravitationally stable. A planet could orbit it, perhaps with energy provided by internal heat or nearby stellar companions. Some speculative models even suggest that the radiation emitted from a low-rate accretion disk might be enough to warm a planet's surface, provided the planet's distance and atmospheric composition were well-tuned. These are extreme cases, but they challenge our understanding of what sunlight even means. On a broader scale, the presence of a quasar can shape star formation across an entire galaxy. The outflows and jets from the active nucleus can compress gas clouds, triggering bursts of star formation in certain regions, while blowing away gas in others, quenching star birth entirely. This feedback mechanism is one reason quasars are of intense interest in the field of galaxy evolution. They are not mere anomalies, they are formative events in the life of a galaxy. And so any planets that form during or after a quasar phase are indirectly shaped by its energy. Quasars are also crucial to our understanding of the early universe. Because they are so luminous, they can be seen across cosmic time. The most distant quasars discovered so far date back to less than 1 billion years after the Big Bang. Studying them gives astronomers insight into the growth of structure, the formation of the first massive black holes, and the reionization of the intergalactic medium. These ancient beacons reveal a universe that was once far more violent, far more chaotic, and far more dynamic than the calm spiral arms we observe today. Despite their luminosity, quasars are not eternal. Eventually, the black hole exhausts its supply of nearby gas and dust or stabilizes due to angular momentum barriers. The accretion disk dissipates, the jets vanish, the light fades. What remains is a dormant supermassive black hole, invisible, inert, but still there, lurking at the center of its galaxy. Many galaxies that appear quiet today may have once harbored quasars. The energy released during those active phases may still echo through the stars and the interstellar medium long after the light has gone out. The idea of a sun that does not emit light on its own is conceptually difficult, but astrophysically consistent. A black hole can shape orbits, guide the formation of planets, influence chemistry through radiation, and even, under the right conditions, warm distant companions via indirect energy. But it can never be seen directly. It bends light but produces none. Its gravity is palpable, but its face is unknowable. And in that sense, a black hole's sun is perhaps the purest expression of contrast in the cosmos, a center that gives structure but not light, power but not warmth. In recent years, simulations have even considered civilizations harnessing the power of black holes. Concepts like the Penrose process or the idea of a Dyson sphere around an accreting black hole are thought experiments that explore the theoretical limits of energy extraction. While these ideas remain speculative, they point to a future in which intelligent life might not be limited by the presence or absence of traditional stars. Instead, it could adapt to entirely new kinds of energy sources, redefining what a home system even looks like. There is a quiet paradox at the heart of every quasar. It is powered by destruction, the tearing apart of matter, the stretching of atoms into oblivion. And yet, from that destruction comes light. More light than any star can emit, more than billions of stars combined. Quasars illuminate not just the galaxies they inhabit, but the very history of the universe. They are born from collapse, but they serve as lighthouses, guiding us across cosmic time. And so we return to the idea, what if your sun were a black hole? What if the brightest thing in the sky came not from creation, but from falling? What would life be like on a world that orbited darkness, basked in radiation, and understood warmth only as the byproduct of gravity's hunger? Perhaps somewhere, in some future galaxy or distant corner of space, a being looks up into a sky without a sun, watches jets arcing across the stars, and does not fear the blackness. Perhaps they know, as we are only beginning to learn, that even the void can shine, and that not all centers must burn to give meaning. Chapter 4. The Vampire Stars, When One Star Devours Another. The story of stars is often told as one of solitude, brilliant spheres of plasma burning alone in the darkness of space, aging in silence and dying in isolation. Yet in reality, stars are not always solitary. Many are born in pairs or groups, gravitationally bound from the moment they condense from molecular clouds. And in some of these pairings, a darker tale unfolds, one in which one star feeds on another, draining its mass, pulling away its outer layers, and changing the fates of both forever. These are the vampire stars, stellar systems where survival means consumption, and where the distinction between life and death becomes blurred in the gravity-twisted dance of two. The most common type of vampire star is found in what astronomers call a close binary system. In such systems, two stars orbit each other closely enough that their mutual gravitational pull distorts their shapes, stretching them into elongated forms. As stars evolve, their physical size and internal structure change. When one star, often the more massive of the two, reaches the end of its main sequence life, it expands into a red giant. If its companion is nearby, the expanding outer envelope of the giant can cross a boundary known as the Roche lobe. This is the point where the gravitational pull of the companion becomes stronger than that of the giant itself. When material crosses this gravitational boundary, it begins to flow from the red giant to its companion. This mass transfer can happen through a stream of gas that flows from the inner Lagrange point, forming an accretion disk around the receiving star. The donor star, now unable to hold on to its own atmosphere, becomes a hollow shell, a stripped-down core of what it once was. The accreting star, in contrast, becomes more massive, hotter, and sometimes more luminous. It feeds off its partner, growing while the other diminishes, the relationship defined by imbalance. Depending on the mass, distance, and evolutionary stage of the two stars, this process can result in a variety of outcomes. In some cases, the mass transfer is stable and the two stars continue their orbits with new configurations. One bloated and overfed, the other lean and depleted. In other cases, the mass transfer becomes unstable, causing the stars to spiral inward. This can lead to a common envelope phase, where both stars share a single extended atmosphere. Friction within this envelope can cause the stars to lose orbital energy, drawing them even closer until the envelope is ejected entirely. The result is often a tight binary composed of two dense remnants, like a white dwarf paired with a neutron star, or sometimes a complete merger. Astronomers have observed many systems that exhibit these mass transfer behaviors. Algol, one of the brightest stars in the constellation Perseus, is a classic example. The Algol paradox, where the more massive star appears younger and less evolved than its companion, is resolved when one considers that mass transfer has occurred. The once more massive star became a red giant and transferred much of its mass to its partner, effectively rejuvenating it. The donor star, now less massive, appears older and further along in its evolution. This reversal of roles is a key diagnostic of stellar vampirism. Not all accreting stars are obvious to the naked eye. In many systems, especially those involving compact objects like white dwarfs or neutron stars, the accretion process releases immense energy in the form of high-energy radiation. X-ray binaries, for instance, are systems where a neutron star or black hole is siphoning material from a normal star. As this matter spirals inward through an accretion disk, it heats up to millions of degrees, emitting powerful X-rays that can be detected across interstellar distances. These emissions are often variable, flickering or pulsing in response to changes in accretion rate or magnetic field structure. In white dwarf accretors, the mass transfer can trigger thermonuclear explosions on the surface of the white dwarf. As hydrogen from the donor star builds up on the surface, pressure and temperature rise until a runaway reaction occurs, releasing a sudden burst of energy. These outbursts are known as novae, stellar flares that can increase a system's brightness by a factor of 10,000 or more. In some cases, the white dwarf accumulates enough mass to reach the Chandrasekhar limit, the maximum mass a white dwarf can sustain. Beyond this point, it collapses into a neutron star or explodes entirely as a Type Ia supernova. This latter scenario is particularly significant for cosmology. Type Ia supernovae are used as standard candles to measure cosmic distances because their peak brightness is remarkably uniform. But their origins, in mass transfer binaries involving white dwarfs, are rooted in this violent parasitic process. The destruction of a star is made possible by the persistent feeding of its partner, a grim yet efficient mechanism in the grand narrative of stellar evolution. In rare configurations, the roles can reverse. The initially smaller star, after gaining enough mass from its partner, may eventually evolve faster and begin its own expansion phase, transferring material back to the donor. This can lead to a kind of oscillating exchange, a prolonged interaction where each star shapes the fate of the other across hundreds of millions of years. The balance is delicate, and small perturbations in mass or orbital separation can tip the system into merger or destabilization. One of the most fascinating outcomes of these close interactions is the potential formation of exotic objects. When two white dwarfs merge, they may form a single massive white dwarf or ignite into a supernova. When a neutron star consumes too much material, it may collapse into a black hole. In every case, the evolutionary path is altered, sometimes violently, sometimes subtly, by the gravitational theft occurring between stars. The dynamics of vampire star systems also raise questions about angular momentum. As mass moves from one star to another, it carries angular momentum with it. The redistribution of this momentum can cause the accreting star to spin faster, sometimes approaching breakup speeds. In rapidly spinning neutron stars, this process can create millisecond pulsars, compact remnants that rotate hundreds of times per second, emitting beams of radio waves with clock-like precision. These objects are the end products of stellar cannibalism, their rapid rotation preserved by the momentum of stolen mass. From an observational standpoint, vampire stars offer unique signatures. Doppler spectroscopy can reveal wobbles in the radial velocity of the stars, indicating orbital motion. Photometric surveys detect periodic dips in brightness as the stars eclipse each other. Spectroscopic analysis shows broadened or shifted absorption lines, and in some systems, emission lines from hot accretion disks or jets. Multi-wavelength observations, from radio to gamma rays, are often required to piece together the full story of these systems. Beyond individual cases, stellar vampirism has broader implications for the population dynamics of galaxies. Mass transfer binaries contribute to the chemical enrichment of the interstellar medium, particularly through supernovae that release elements like iron and nickel. They also play a role in the formation of compact object binaries, which are the progenitors of gravitational wave events. The merger of two neutron stars, first detected in 2017 as GW0817, likely began as a pair of stars that exchanged mass, spiraled inward, and ultimately collided in a spectacular burst of gravitational and electromagnetic radiation. These systems challenge our intuition about identity and evolution. In most forms of life, to grow stronger by draining in another is an act of predation or parasitism. In stars, it is a mechanism of transformation. The donor star loses itself in the process, but the accretor is changed too, not just more massive, but often more active, more dangerous, or more short-lived. Their shared fate is not linear but recursive, with cause and effect braided together by gravity and thermodynamics. And yet, even in this predatory intimacy, there is elegance. Two objects, born of the same cloud, evolve not in isolation, but in tandem. They influence one another not just gravitationally, but through direct transfer of mass, heat, and angular momentum. Their lives are entangled, their deaths often mutual. They are not solitary wayfarers, but partners in a cosmic rite, one that can lead to brilliance, destruction, or quiet extinction. Somewhere in the galaxy, a star is feeding on its companion, growing bright with stolen energy, unaware or indifferent to the fact that its light is borrowed. Somewhere else, a stripped core cools in silence, hollowed and dim, circling the partner that consumed it. And in this way, the cosmos tells a story not only of creation and collapse, but of consumption, of stars that do not burn alone, but thrive in the balance of give and take. Chapter 5: Eternal Twilight. Life around a dying red dwarf. The term sunlight evokes a warm golden glow, It conjures memories of bright days, blue skies, and the daily rhythm of life tied to the rising and setting of our yellow-white G-type star. But if our planet orbited a red dwarf, sunlight would mean something entirely different. The light would be dim, the sky a muted hue, and the day, if it existed at all, might stretch indefinitely into a kind of perpetual dusk. These small stars, the most numerous in the galaxy, offer a different vision of stellar life, one slower, dimmer, but far more enduring. Red dwarfs, or M-type stars, are the smallest and coolest stars that can sustain hydrogen fusion in their cores. They typically have masses between 0.08 and 0.6 times that of the Sun and radiate with a fraction of its luminosity, often less than 1%. Their surface temperatures range from about 2,400 to 3,700 Kelvin, making them far cooler than the Sun and shifting the peak of their radiation toward the red and infrared parts of the spectrum. They do not shine with fierce brilliance. Instead, they smolder, faintly, steadily, and for a very long time. In fact, red dwarfs are among the most long-lived objects in the universe. Because they are fully convective, meaning their interiors mix thoroughly from core to surface, they burn through their hydrogen fuel with remarkable efficiency. While a star like the Sun will exhaust its core hydrogen in about 10 billion years, a red dwarf can shine for hundreds of billions, even trillions of years. That is far longer than the current age of the universe, which means that no red dwarf has yet reached the end of its life. They are, in a sense, the youngest old stars we know. Ancient in formation, but still burning as if they've only just begun. Planets orbiting red dwarfs occupy a very different kind of habitable zone. Because the star emits so little light, the region where a planet could maintain liquid water on its surface lies much closer in, often just a few % of an astronomical unit. At such short distances, orbital periods shrink dramatically. A year on one of these worlds might last only a few days or weeks. And due to the proximity, many of these planets are expected to be tidally locked, with one hemisphere always facing the star while the other remains in permanent darkness. This tidal locking has profound implications for climate and habitability. The day side may experience constant light and modest warmth, while the night side could plunge into deep cold, potentially freezing out the atmosphere if circulation is weak. However, recent climate models suggest that a thick enough atmosphere, particularly one rich in carbon dioxide or other greenhouse gases, could distribute heat effectively between hemispheres. Oceans, too, could act as thermal regulators, carrying warmth from the day side to the night through large-scale currents. In this way, even a tidally locked planet could host stable conditions, not global, but regional, with temperate twilight zones along the terminator line. The light on such a world would be distinctly different from Earth's. A red dwarf's output skews toward longer wavelengths, with less visible blue and more infrared. Plants, if they evolved, might rely on pigments tuned to this dimmer spectrum. Rather than green, they might appear dark purple or even black, maximizing absorption in low light conditions. Photosynthesis itself would need to be reconfigured to take advantage of the faint glow, and perhaps operate more slowly or intermittently. Life would not chase the sun's arc across the sky because there would be no arc. The sky might never brighten beyond a soft red sheen. One of the key challenges for life around red dwarfs is the activity of the star itself. While they burn quietly for eons, many red dwarfs are magnetically active, especially in their youth. Stellar flares, sudden bursts of high-energy radiation, can erupt frequently, bombarding nearby planets with X-rays and ultraviolet light. These flares are sometimes accompanied by coronal mass ejections, which can strip planetary atmospheres over time if a strong magnetic field is not present. In tightly bound orbits, planets are more exposed to this radiation, and their own rotation rates may be slowed, weakening their magnetic shields. Despite these hazards, red dwarf systems have become a primary focus of exoplanet research, especially in the search for Earth-like worlds. Their small size and low luminosity make it easier to detect transiting planets. A planet passing in front of a red dwarf blocks a larger fraction of its light, creating a stronger signal. Likewise, the gravitational tug of even a small planet is more detectable via radial velocity methods. Several notable systems have already captured scientific and public attention. TRAPPIST-1, located just 40 light-years away, is a red dwarf hosting at least 7 Earth-sized planets, 3 of which lie within the star's habitable zone. These planets orbit with periods ranging from 1.5 to 19 days, and their densities suggest rocky compositions. While the ultimate habitability of these worlds remains uncertain, especially given TRAPPIST-1's flare activity, they demonstrate the potential for complex planetary systems around even the faintest of stars. Another intriguing case is Proxima Centauri b, an exoplanet orbiting the closest star to our solar system. Proxima is a small red dwarf, and its planet lies within the habitable zone with an orbital period of just 11.2 days. While the star is known for frequent flaring, Proxima b remains one of the most promising targets for future direct imaging and atmospheric analysis. Its proximity makes it an ideal candidate for future missions, including those that might one day send robotic probes. The potential for life around red dwarfs also opens a philosophical perspective on the future of life in the universe. As larger stars burn out over the coming billions of years, red dwarfs will remain. Long after the sun becomes a white dwarf, long after its planets are frozen and dark, red dwarfs will still glow softly in the night. If intelligent life evolves around them or migrates to them, these stars may host the final sparks of biology in a darkening cosmos. In the far future, when galaxies dim and entropy reigns, life may persist under skies that never knew true daylight, only twilight. Red dwarf stars will likely dominate the stellar population of the deep future. As the more massive stars vanish, either through supernova or quiet extinction, the universe will grow quieter, redder, and more uniform. The galaxies of tomorrow may appear dim and sallow, not because light has vanished, but because it burns so gently and so slowly. And yet, in that vast cosmic stillness, red dwarfs will remain as guardians of persistence, not dramatic or powerful, but unrelenting. Their very slowness is their gift. By burning their fuel at a crawl, by spreading their light across eons, they ensure that time stretches forward for those who dwell in their orbit. They offer a stability that our own sun cannot. No violent swelling into a red giant, no supernova. Just a gentle fading, billions of years after even the memory of Earth is gone. The landscapes of such planets would reflect that long stillness. With no seasons in the traditional sense, and with the same face always turned to the sky, geology and climate would be sculpted not by the rhythm of a spinning world, but by the slow breathing of atmosphere and crust. Ice might persist in the nightlands for hundreds of millions of years. Deserts on the dayside might be baked not by heat, but by stagnation. A stillness that denies movement, not one that burns. Civilizations that arose there might never know nightfall or sunrise. Time would be measured in different ways, by changes in stellar output, by wind patterns, by the occasional planetary transit. Architecture might always face one way. Light and dark would be places, not times. And culture itself might evolve with a deep sense of permanence, of continuity, not broken by rotation, but stretched by stillness. And in all of this, there is something haunting. That in the darkest, quietest places in the galaxy, there could be life. Not in the warm glow of a golden sun, but in the soft red hush of eternal twilight. That consciousness, if it emerged, would not look up at a rising sun, but simply exist, always bathed in a faint glow, never seeing more than a narrow slice of sky. Perhaps the most poetic truth about red dwarfs is this: they will outlive the universe we know. When galaxies are empty and the stars we see today are long dead, red dwarfs will remain. Their light will still trace the outlines of alien worlds, and maybe on one of those worlds, something will open its eyes to the red horizon and wonder what it means to live in the final act of time. Chapter 6. Flare stars, where the sun burns with anger. In the human imagination, stars are constant things. They flicker in the distance, perhaps, but they do not change. They offer reliable light, unvarying warmth, a fixed background against which time passes. Our own sun follows this rhythm. Though it does flare and fluctuate slightly in brightness over time, those changes are measured in fractions of a percent, and their impact on Earth's habitability is minimal. But not all stars are so calm. In many systems scattered across the galaxy, stars erupt with sudden violence, releasing immense energy in seconds, altering their immediate environments with each outburst. These are flare stars, celestial bodies that burn not with steady fire, but with intermittent rage. A flare star is typically a low-mass star, most often an M-type red dwarf, whose magnetic activity produces sudden, dramatic increases in brightness. These flares are not just optical events. They involve the release of energy across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. The increase in luminosity during a flare can exceed several times the star's baseline brightness, and in some cases can be observed from Earth despite the star's intrinsic faintness. The physical mechanism behind these flares is rooted in stellar magnetism. Like the Sun, flare stars possess magnetic fields generated by the movement of charged particles within their convective zones. But unlike the Sun, many of these stars are fully convective, meaning their entire volume circulates, allowing for more uniform and often stronger magnetic field generation. When magnetic field lines become twisted or tangled due to differential rotation or other instabilities, they can suddenly snap and reconnect, releasing stored magnetic energy in a rapid burst. This process, known as magnetic reconnection, is what powers solar flares, and in flare stars, it operates at even greater intensities. The flare itself is an explosive event. Charged particles are accelerated to near relativistic speeds, colliding with atoms in the stellar atmosphere and heating them to tens of millions of degrees. This produces intense X-ray and ultraviolet radiation, which radiates outward at the speed of light. Meanwhile, high-energy protons and electrons stream outward into the surrounding space, creating shock waves and particle storms that can extend far beyond the star's surface. In a matter of minutes, the space around the star becomes hostile, bombarded by radiation capable of disrupting planetary atmospheres and sterilizing surfaces. Unlike the Sun, where flares are relatively rare and follow an 11-year activity cycle, many flare stars erupt with startling frequency. Some emit flares every few hours, with little warning and no consistent pattern. This level of activity is particularly common in younger red dwarfs, whose rapid rotation and strong magnetic fields make them highly unstable. As the star ages and slows down, its flare activity generally decreases, but some stars remain active for billions of years, especially if tidal interactions with close companions keep them spinning rapidly. The implications for planetary habitability around such stars are profound. Many of the most promising exoplanet systems discovered so far orbit red dwarfs, stars like Proxima Centauri and TRAPPIST-1, due to the relative ease of detection via the transit and radial velocity methods. But these same stars are among the most flare-active known. Proxima Centauri, for instance, produces flares powerful enough to increase its brightness by a factor of 10 in the ultraviolet in under 10 seconds. In one 2018 observation, Proxima released a flare hundreds of times stronger than any recorded solar flare, an event that would have obliterated the ozone layer on any Earth-like planet in its habitable zone. Even planets with atmospheres may not be safe. Repeated flare activity can erode a planet's protective gases over time, especially if the planet lacks a strong magnetic field to deflect incoming charged particles. Without protection, the upper atmosphere can be ionized and gradually stripped away, reducing pressure, altering climate, and in extreme cases, rendering the surface uninhabitable. Ultraviolet radiation can also photodissociate molecules like water, breaking them apart into hydrogen and oxygen, with the hydrogen eventually escaping into space. Over long timescales, this could dehydrate a planet entirely, even if it began with abundant liquid water. Yet the picture is not entirely bleak. Some planetary configurations may mitigate the damage. A thick, Venus-like atmosphere could absorb much of the radiation and allow surface temperatures to remain stable. An ocean-covered world might shield life below a few meters of water. Subsurface biospheres, like those found near hydrothermal vents on Earth, would be largely immune to surface radiation. And planets with powerful magnetic fields, possibly generated by internal convection or tidal heating, could repel many of the charged particles before they reach the atmosphere. There is also the possibility that flare activity might contribute to prebiotic chemistry. On early Earth, ultraviolet light likely played a role in forming complex organic molecules by breaking bonds and creating reactive intermediates. Flares could serve a similar function, providing intermittent pulses of energy that catalyze chemical evolution. However, this requires a delicate balance. Too little radiation and complex molecules may never form. Too much, and they are destroyed as quickly as they arise. From an observational perspective, flare stars are both a challenge and an opportunity. Their variability complicates the search for exoplanets, as flares can mimic or obscure transit signals. But they also offer a chance to study extreme space weather in real time. The flare frequency of a given star is often tied to its rotation rate and age. Young stars, especially in open clusters, spin rapidly and flare often. As they age, magnetic braking slows them down, reducing both flare energy and frequency. This means that stellar activity can be a proxy for stellar age, a technique known as gyrochronology. By measuring the rotation period and flare rate, astronomers can estimate how long a star has been burning. This, in turn, informs models of planetary system evolution and habitability. There are even rarer and more extreme cases of flare activity. Some stars, known as superflare stars, exhibit eruptions thousands of times more energetic than anything seen on the Sun. These events, while infrequent, could have devastating effects on nearby planets, including stripping atmospheres, igniting chemical fires, or inducing mass extinctions. The Sun itself may be capable of such events on geologic timescales, though no clear superflare has been recorded in human history. Tree ring data and ice cores suggest possible candidates, but the question remains open. For civilizations that might evolve around such stars, the sky would be a source of both sustenance and danger. The primary source of light would be inconsistent, sometimes dim and peaceful, sometimes searing with radiation. Daylight might come in pulses or be interrupted by moments of sudden, blinding brightness. Cultural adaptations might arise. Myths surrounding sudden bursts of celestial rage, architectural designs built to shield against invisible storms, calendars measured in flare intervals rather than seasons. In this volatile setting, technology would need to advance quickly to ensure survival. Atmospheric monitoring systems, underground refuges, radiation-hardened infrastructure, all might be necessary for long-term stability. Space travel could be especially hazardous, with flares capable of disabling electronics and threatening astronauts within minutes. And yet, for all the danger, such a civilization might also find beauty in the turbulence, seeing in each flare not destruction, but expression, a stellar heartbeat echoing through space. There is an ancient silence in most of the stars we see. They flicker, they rotate, but they do not scream. Flare stars are different. They do not whisper their power, they shout it, abruptly and without apology. Their light is not constant, but explosive. Their love, if one could call it that, is not gentle warmth, but searing energy, doled out in unpredictable bursts. And perhaps there is something poetic in that some stars live fast and wild, burning not with steady calm, but with restless pulses. That in the deep quiet of space, there are places where the sun is not a source of comfort, but a force to be survived. That even in the heart of chaos, a planet might hold on. And maybe somewhere, beneath a sky that burns with anger, life has found a way to thrive. Not despite the fire, but because of it. Chapter 7. Planets of the Pulsar, dead stars that still shine. When we think of stars, we imagine vast spheres of incandescent gas, fusing hydrogen into helium and radiating energy across the cosmos. A star is, by definition, a source of light and heat, a sustained thermonuclear engine holding gravitational collapse at bay. But not all stars fit this mold. Some have burned through their fuel, collapsed into dense remnants, and yet continue to shine in their own strange, rhythmic way. These are pulsars, the remnants of massive stars that ended their lives in supernova explosions. Though dead by the standards of nuclear fusion, they remain luminous in another sense, emitting beams of electromagnetic radiation that sweep across space like the beams of a cosmic lighthouse. Pulsars are a specific class of neutron stars, themselves born from the collapsed cores of massive stars that once burned hot and bright. When such a star exhausts its nuclear fuel, it can no longer support itself against gravity. The result is a violent implosion followed by a supernova explosion. What remains is a compact object, no more than about 20 kilometers in diameter, composed almost entirely of neutrons. A single teaspoon of neutron star material would weigh about 1 billion tons. Yet, despite their tiny size, pulsars often possess greater mass than the Sun. What makes pulsars unique among neutron stars is their rapid rotation and strong magnetic fields. As they spin, their magnetic poles, misaligned with their rotation axis, emit beams of radiation, usually in radio frequencies, but sometimes also in optical, X-ray, and gamma-ray wavelengths. If Earth lies within the path of these beams, we observe a periodic pulse of light, typically hundreds of times per second. This precision is so regular that some pulsars rival atomic clocks in their stability, making them valuable tools in timekeeping and astrophysical navigation. It may seem counterintuitive then to speak of planets around such violent objects. After all, pulsars are born in cataclysm. The supernova that forms a neutron star releases enough energy to blow away any nearby planets, vaporize atmospheres, and reset the local space environment. The radiation environment around an active pulsar is harsh, awash in high-energy particles, X-rays, and magnetic turbulence. Yet despite this, planets have been found orbiting pulsars. These worlds are among the strangest in the galaxy, gorged or reformed in the shadow of a stellar corpse. The first confirmed detection of an exoplanet occurred not around a sun-like star, but around a pulsar. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the discovery of 2 planets orbiting PSR B257+12, a millisecond pulsar located approximately 2,300 light-years from Earth. A third, smaller planet was confirmed shortly thereafter. These planets are rocky, roughly Earth-sized, and orbit the pulsar at distances comparable to those of Mercury and Venus in our solar system. Yet their existence defied expectations. How could such planets survive or form in the wake of a supernova? Several theories have emerged to explain the origins of pulsar planets. One possibility is that they are second-generation planets, formed from a disk of fallback material left over after the supernova explosion. This material could cool and coalesce into a new planetary system, much like a miniature version of the original protoplanetary disk. Another possibility is that the pulsar acquired material through the disruption of a binary companion, a star that was partially or completely destroyed in the process of the supernova or through later mass transfer. In this scenario, the debris from the shredded companion might settle into a disk and seed the formation of new planets. Regardless of their origin, the environments these planets inhabit are extreme. The pulsar's radiation, while beamed and directional, creates an electromagnetic landscape unlike anything experienced in our own solar system. The planets are bathed in a steady pulse of high-energy photons and relativistic particles. Their surfaces, if exposed, would be scorched and irradiated beyond recognition. Atmospheres, if they ever existed, might be long gone unless replenished by internal volcanic outgassing or protected by powerful magnetic fields. But these planets are not merely academic curiosities. Because pulsars are so regular in their rotation, any gravitational influence from orbiting bodies causes measurable variations in the timing of their pulses. This allows astronomers to detect even small planets with high precision, down to masses much smaller than Earth's. In some cases, the presence of multiple planets allows for dynamic modeling of their interactions, leading to mass and orbital determinations that rival those of any known exoplanetary system. Another extraordinary case is Pulsar B1620-26b, a planet orbiting a neutron star white dwarf binary system in the globular cluster M4. Often called the Methuselah planet, due to its estimated age of over 12 billion years, it is among the oldest planets known. Its continued existence suggests that planetary systems can persist or reform even in the tumultuous environments of dense star clusters and compact object binaries. This resilience challenges traditional models of planetary formation and stability, pushing the boundaries of where we expect life-supporting worlds to reside. Despite their seemingly hostile nature, some scientists have speculated, however cautiously, about the habitability of pulsar planets. While surface life seems improbable due to the intense radiation, subsurface environments might offer more favorable conditions. If a pulsar planet has a thick crust and internal heat sources such as radioactive decay or tidal flexing, it could sustain subsurface oceans or geothermal pockets. These niches, isolated from the hostile exterior, might resemble environments on Europa or Enceladus in our own solar system, where life is theorized to be possible beneath icy shells. The question of long-term orbital stability in pulsar systems is particularly important given the immense gravitational forces and energetic environment near these neutron stars. Unlike planets around main sequence stars, pulsar planets must contend with a highly compact central mass, relativistic winds, and, in some cases, a complex gravitational tug from binary companions like white dwarfs or other neutron stars. Despite these challenges, simulations suggest that planetary orbits can remain stable for billions of years, provided they form at safe distances beyond the reach of the pulsar's accretion activity and avoid close orbital resonances that might lead to destabilization. Moreover, the process of planet formation around pulsars may not follow the conventional steps seen in protoplanetary disks around young stars. Instead of forming from the gradual coalescence of dust in a cool, quiescent disk, pulsar planets may emerge from highly processed metal-rich material. The supernova explosion or the disruption of a binary companion injects elements like iron, nickel, and silicon into the debris field. These heavy elements, condensed in extreme conditions, might facilitate the rapid formation of rocky planets, denser and possibly more geologically active than their solar system counterparts. This could mean that pulsar planets, though rare and hostile, are chemically rich worlds with complex internal evolution. There are also speculative scenarios in which advanced civilizations might harness the energy of pulsars. The precision of their pulses makes them ideal for interstellar communication and navigation, and the relativistic jets and magnetic fields could, in theory, be used as enormous energy sources. Dyson sphere analogs or orbital structures could be imagined, not to trap light as with traditional stars, but to extract usable power from the pulsar's rotation or magnetosphere. While purely hypothetical, these ideas have inspired science fiction and the search for technosignatures in pulsar timing anomalies. Observationally, pulsars are studied across the entire electromagnetic spectrum. Radio telescopes detect the pulses themselves, while X-ray and gamma-ray observatories monitor high-energy emissions from hotspots and accretion disks. The timing of pulses is tracked over years and decades, allowing astronomers to measure not only planetary companions, but also gravitational waves, interstellar medium properties, and fundamental constants. In recent years, pulsar timing arrays have become a critical tool in the search for low-frequency gravitational waves, ripples in space-time caused by orbiting supermassive black holes in distant galaxies. What pulsar planets teach us, ultimately, is that planetary systems are more diverse than we ever imagined. They do not require the gentle glow of a sun-like star, nor the calm stability of a quiet neighborhood. They can form, survive, and perhaps even thrive around the most unlikely hosts, including the collapsed, magnetized core of a star that once exploded with more energy than billions of nuclear bombs. If planets can form in the wake of such destruction, and if they can orbit for millions of years without being ejected or vaporized, then our assumptions about the limits of nature must be revised. These systems also challenge our ideas about beginnings and endings. A pulsar is a stellar corpse, a remnant of death, and yet around it, matter has gathered into coherent shapes. Gravitational stability has emerged from chaos. Time itself, in the form of precisely measured pulses, flows more regularly than in any human-made machine. From the ruins of a star, order arises again. And maybe, just maybe, something could exist there. Not in the light, but in the rhythm. Not under a warm sun, but beneath the clockwork flash of a dying beacon. Perhaps life, or memory, or curiosity does not need daylight, only a reason to continue. In a universe full of fire, perhaps there is also room for those who live in the ashes. Chapter 8. Circumbinary Worlds. Orbiting two suns at once. In our imagination, the notion of two suns rising and setting in unison conjures scenes of exotic skies, like the famous sunset on Tatooine in science fiction. But beyond cinematic imagery, such star systems are not fantasy. They are real, and they are far more common than once believed. Among the many surprises delivered by modern exoplanet science is the confirmation that planets can, and do, orbit two stars at once. These are known as circumbinary planets, worlds that revolve not around a single sun, but around a pair of stars dancing in gravitational partnership. Binary stars are abundant in the galaxy. In fact, roughly half of all sun-like stars are part of binary or multiple star systems. In a binary system, two stars orbit their common center of mass, locked in a gravitational waltz. In the past, it was assumed that this constant motion would create an environment too unstable for planet formation. The chaotic gravitational forces between two stars were thought to disrupt the delicate process by which dust and gas clumped together into planets. But observations have proved this assumption wrong. Not only do circumbinary planets exist, but in some systems, they appear to be remarkably stable, resilient, and even Earth-like in their mass and composition. The Kepler Space Telescope played a crucial role in discovering these planets. Among its most famous finds is Kepler 16b, the first confirmed planet to orbit two stars. Located about 200 light-years away, Kepler 16b is a gas giant roughly the size of Saturn. Its orbit traces a nearly circular path around a pair of stars, one similar in size to our Sun, the other a red dwarf. As these two stars orbit each other, the planet orbits them both, never veering too close to one or the other. The result is a stable circumbinary orbit where the gravitational influence of both stars is felt equally. What makes these systems unique is the way gravity shapes both planetary formation and orbital dynamics. In a single star system like our own, a protoplanetary disk forms around a young star, allowing dust and gas to gradually assemble into larger bodies. In circumbinary systems, the disk must encircle both stars. The stars themselves stir this disk with their motion, carving out a central gap near their orbits. Beyond this gap, however, conditions can become surprisingly hospitable for planet formation. Once a planet forms at a safe distance, typically about 2 to 4 times the separation between the stars, its orbit can remain stable for billions of years. From the surface of such a world, the sky would be unlike anything we know. Depending on the mass, temperature, and distance of the stars, a planet might experience complex patterns of daylight. There would be times when both stars rise and set together, bathing the planet in double light. At other times, one star might eclipse the other, casting partial shadows or creating long periods of soft illumination. If the stars are of different colors, one yellow-white, the other red, the resulting hues in the sky would shift in subtle, beautiful ways. Days and nights might not follow a regular pattern, especially if the stars are eccentric in their orbit. The variation in heat and light could lead to unique seasonal dynamics, affecting everything from atmospheric circulation to cloud formation. Some circumbinary planets are located within their system's habitable zones, the region where temperatures could allow liquid water to exist. Kepler-47c, for instance, orbits within the habitable zone of its binary system. While it is likely a gas giant, any large moons it possesses could potentially be habitable in principle. This opens up the possibility that life might one day be found not on the planet itself, but on a satellite orbiting a planet that orbits 2 suns. It's a nested system of motion, each level adding complexity, but also possibility. The climate on such a world would be dynamic. The dual star illumination would produce a different energy input than Earth experiences. At times, the 2 stars could combine their radiance, causing temperature spikes. At other times, their positions could lead to prolonged cooling if one blocks the other, or they set at staggered intervals. This irregularity could drive intense weather systems or influence how life, if it emerged, might adapt to cycles that are less predictable than Earth's day-night rhythm. Plants, for instance, would need to evolve photosynthetic strategies that account for variable light intensities and spectral qualities. The stability of circumbinary planets also depends on their distance from the binary pair. Too close, and the gravitational tug-of-war between the stars becomes too intense, destabilizing orbits and preventing long-term survival. Too far, and the stars act more like a single-point source, reducing the unique gravitational characteristics that define such systems. There exists a critical radius beyond which stable circumbinary orbits become possible. This region is shaped by the mass ratio of the stars, their separation, and the eccentricity of their orbit. Interestingly, planets that form within circumbinary disks may migrate inward after formation, moving through the disk toward the central stars. This inward migration is thought to halt at the edge of the unstable zone, essentially forming a natural orbital boundary. Many of the circumbinary planets discovered so far, including Kepler-16b and Kepler-34b, orbit just beyond this threshold, suggesting that migration plays a critical role in their final positioning. These systems are not merely static, they are shaped by dynamic interactions over time, gravitational nudges, resonance effects, and even the drag of gas and dust. The very act of planet formation in such systems raises fascinating questions about how resilient matter can be. Despite the constant churning of the binary stars and the turbulence of their surrounding disk, the process of accretion still manages to build coherent, stable worlds. The disk's particles do not simply scatter or fall into the stars. Instead, through collisions, clustering, and angular momentum exchange, they give rise to worlds. The same chaotic forces that might seem to prevent formation instead seem to sculpt it, not by avoiding disruption, but by evolving within it. Circumbinary planets also provide a natural laboratory for studying orbital mechanics and celestial stability. The orbital periods of these planets are influenced not only by the binary's mass, but also by periodic gravitational perturbations. These can cause precession of the orbit or shifts in eccentricity over time. Some planets exhibit transit timing variations, slight changes in the expected moment they cross in front of their stars, which can provide detailed clues about their mass and orbital resonance. These subtle interactions give astronomers rare insights into the complex choreography of multi-body systems. More than just academic curiosities, circumbinary planets challenge the assumption that life-bearing systems must resemble our own. The rare Earth hypothesis, which argues that life depends on a quiet, single-star environment, may need to be rethought in light of these discoveries. If stability and liquid water are possible even in binary systems, then the range of habitable zones across the galaxy might be wider than previously believed. Circumbinary systems remind us that Earth is not the template, but merely one instance of what nature permits. Even in their formation, these planets seem to defy easy categorization. Some may arise from coalescing gas and dust in a circumbinary disk. Others may be captured from elsewhere, rogue planets pulled in by the star's gravity. And still others may form after dramatic events like stellar mergers or the disruption of a third companion. Their diversity, both in origin and in orbital behavior, mirrors the creative chaos that defines the cosmos. From a philosophical perspective, circumbinary worlds reflect something deeper about the universe: its refusal to follow a single path. Where we might expect destruction, we find harmony. Where complexity might suggest disorder, we observe structure. Two stars spinning around each other might seem like a recipe for chaos, but in reality, they can foster systems of great balance and grace. Planets orbit not in fear of disruption, but in synchrony with the dual heartbeat of their parent stars. And on one of those worlds, under skies lit by two suns, some distant being might one day look up and wonder what it means to be warmed by more than one light. To grow not in the glow of a single source, but in a spectrum of balance and motion. To live in a world shaped not by stability alone, but by the resilience that comes from adapting to something more complex and more beautiful. Chapter 9. Stars that eject planets when gravity goes rogue. When we picture planets orbiting stars, we tend to think in terms of harmony, a serene clockwork dance where gravity binds each body to its place. The star sits at the center, exerting a gentle yet firm gravitational pull, and the planets circle it in orderly paths, year after predictable year. Our solar system reinforces this image with its relatively stable orbits and quiet evolutionary history. But the wider galaxy tells a more chaotic story. In many star systems, the pull of gravity doesn't just bind, it can expel. Planets can be tossed away, flung out of their birthplaces by the very gravitational forces that once held them close. These are not rare flukes. Planetary ejection is a natural outcome of the complex, volatile process of planetary system formation and evolution. The mechanics of planetary ejection stem from fundamental gravitational interactions. When multiple planets form around a star, they do so in a disk of gas and dust. Over time, these planets interact gravitationally with each other, exchanging angular momentum and subtly tugging on one another's orbits. In a system with many massive planets or planets in resonant configurations, these interactions can become unstable. One planet may spiral inward while another is thrown outward. If a planet gains enough energy from such an encounter, it can be launched past the system's escape velocity, the minimum speed needed to break free from the star's gravity. Once that threshold is crossed, the planet is no longer bound. It becomes a rogue, a free-floating body drifting through interstellar space. This kind of instability is especially likely in young planetary systems. In their early stages, planetary orbits can be eccentric, overlapping, or poorly spaced. Over time, gravitational nudges accumulate, and close encounters between planets can disrupt even seemingly stable configurations. Computer simulations show that many systems are inherently chaotic, especially those with multiple gas giants. In some models of early planetary evolution, more than half of initially formed planets are ejected within the first 100 million years. Our own solar system may bear the scars of such an event. The hypothetical existence of a fifth giant planet that was once part of the system but later ejected during a reshuffling of orbits. Ejection can also be triggered by external influences. A nearby passing star can perturb a planetary system, especially in dense star-forming regions like stellar nurseries or open clusters. These gravitational nudges might not unbind planets directly, but they can destabilize orbits, setting the stage for later interactions among planets to escalate into full ejection events. In some cases, binary stars or massive companions like brown dwarfs can disrupt planetary orbits if their own orbits evolve over time, leading to a dynamic environment where ejection is not only possible, but likely. Even the migration of planets within their own disks can lead to ejections. As massive planets move inward through the disk, a process driven by interactions with the gas and dust, they can shepherd or scatter smaller bodies. These interactions can toss other planets into eccentric orbits or fling them entirely out of the system. The inward movement of Jupiter in the early solar system, for example, is thought to have disturbed many smaller bodies in the inner disk, possibly preventing the formation of a super-Earth and contributing to the asteroid belt structure. In more extreme cases, a migrating gas giant can clear its entire orbital neighborhood, leaving behind a sparse or radically rearranged planetary architecture. Observationally, the most compelling evidence for ejected planets comes from surveys that search for faint, slow-moving objects in the galaxy. These rogue planets, unbound to any star, do not emit their own light, but they can be detected through gravitational microlensing, a technique that relies on the bending of light from background stars when a massive object passes in front of them. The discovery of free-floating planets has profound implications. It suggests that planet formation is far more dynamic than the traditional, orderly model. Planets are not guaranteed a permanent home. Their fate can depend on chance encounters, small shifts in gravitational balances, or the presence of a larger neighbor. In some cases, a single misstep, a close pass with a giant planet, an unlucky resonance, or a perturbation from a passing star can end a planet's relationship with its sun forever. There are also curious consequences for the ejected planets themselves. Without a star, they no longer experience day or night. Their temperatures drop rapidly unless internal heat, from radioactive decay or residual formation energy, keeps them warm. Some large rogue planets may retain thick atmospheres, capable of insulating them and perhaps maintaining subsurface oceans, especially if tidal heating is involved via a captured moon or orbital eccentricity from a prior system. Though the surface would be cold and dark, the interior might remain geologically active for billions of years. This raises fascinating, though speculative, questions about whether life could exist on such worlds, especially in protected subsurface environments. These planetary nomads may be dark, but they are not necessarily lifeless. From a galactic perspective, rogue planets could outnumber stars. If ejections are as common as simulations suggest, the galaxy could be teeming with unbound planets. Some estimates propose that for every star in the Milky Way, there may be one or more free-floating planets, adrift, silent, and invisible, except to the most sensitive instruments. These invisible travelers form an unseen population, reminding us that our observations capture only a fraction of what truly exists. Even in systems where planets are not fully ejected, close encounters can still send them into highly elliptical orbits. These planets may swing close to their star for brief periods, only to slingshot far out into the dark for centuries before returning. Such eccentric orbits create extreme seasonal cycles, with brief moments of light and warmth followed by long ages of freezing darkness. While not technically ejected, these planets live on the edge of gravitational exile, members of a system, but barely. Their tenuous link to their stars mirrors the fragile balance that defines many cosmic structures. Planetary ejection also reshapes the remaining system. When a planet is flung out, it takes angular momentum with it. This can stabilize the orbits of the remaining planets or cause them to shift inward. The architecture of a planetary system, its spacings, resonances, inclinations, is often the fossil record of past violence. A seemingly calm set of orbits may have once hosted chaos, with missing planets now drifting alone through the interstellar void. These processes also blur the line between what we consider a solar system and a planet. If a planet has no sun, is it still a planet? Traditional definitions tie planets to stars, but rogue planets break this mold. They are planetary in mass and origin, but stellar in their solitude. Some may even have moons, atmospheres, or magnetic fields. They may harbor oceans beneath thick ice, volcanism powered by internal heat, or even primitive life forms clinging to the last embers of warmth in a universe of cold. From a broader perspective, these systems highlight the fragility of cosmic order. The forces that build stars and planets are also the forces that scatter them. Gravity is impartial. It binds and it ejects. It creates warmth and throws bodies into the void. It is not malicious, only indifferent. An invisible hand that sculpts galaxies while erasing individual lives. Planets that formed in light may end their journeys in endless night, their histories erased, their skies forever starless. Yet even in this stark view, there is beauty. A rogue planet, floating in darkness, still carries the memory of its creation. Its rocks remember the chemistry of its birth nebula. Its core holds the heat of ancient collisions. Its crust may bear the scars of moons, atmospheres, or oceans long gone. And somewhere, deep in the silence of interstellar space, it continues on. Not orbiting, but still moving. Still part of the galaxy's great story. Perhaps one day, far in the future, our instruments will be sensitive enough to map these lonely wanderers in detail, to trace their trajectories, analyze their surfaces, even imagine what it would be like to stand on a planet with no sunrise. We might learn not just about their past, but about ours, about what makes a planet a home and what happens when home is lost. And in that darkness, we may see ourselves reflected, fragile, drifting, held together by invisible forces. A world that could, with the wrong gravitational nudge, have been one of them. Chapter 10. Galactic Nomads, Planetary Systems Without a Home. When we speak of nomads in the cosmic sense, we often refer to rogue planets, solitary wanderers drifting without the warmth or gravity of a star. But an even more extraordinary idea lies just beyond this. Entire planetary systems, still intact, but no longer gravitationally tethered to any star. These are the galactic nomads, systems born of starlight but exiled into the dark, carrying their planets, moons, and sometimes even asteroid belts through the interstellar void. While no such full system has yet been confirmed observationally, physics tells us they could exist. In fact, they might be more common than we imagine, shaped by the same gravitational turmoil that so often unsettles the universe. To understand how a planetary system could lose its home, we must consider the broader architecture of stellar formation and evolution. Stars form in clusters, born from collapsing clouds of gas and dust. In these crowded stellar nurseries, newborn stars are jostled by gravitational tugs from their siblings. These interactions can be especially violent if massive stars form nearby, as their gravitational influence reaches far and wide. If two forming stars pass close to each other, the gravitational pull can be strong enough to disrupt one or both of their nascent planetary systems. In some cases, a close encounter might strip away a few outer planets. In more extreme cases, it can yank an entire planetary system from its star, leaving it to wander. This process is most likely during the earliest stages of stellar evolution, when orbits are not yet stable and gravitational encounters are frequent. A protostar surrounded by a protoplanetary disk is highly vulnerable. If a nearby massive star sweeps past, it can disrupt the disk or alter the protostar's trajectory. Should the star itself be ejected from its stellar at high velocity, perhaps after a three-body encounter, it could lose mass, lose its planets, or be separated entirely from its system. What remains could be a miniature solar system, no longer orbiting a central sun, but still gravitationally bound to itself. Planets orbiting a failed star, a white dwarf, a brown dwarf, or nothing at all. Another potential pathway to galactic nomadism lies in the realm of stellar death. When a massive star ends its life in a supernova, it can leave behind a neutron star or black hole. The explosion ejects a significant fraction of the star's mass in an instant, reducing the central gravitational force anchoring the system. If the remaining core is not massive enough to retain its planets, they may be flung outward. In some cases, especially if the supernova asymmetry delivers a kick to the stellar remnant, the entire system could be propelled out of its original orbit, escaping not only its local stellar neighborhood but possibly its host galaxy. The result is a planetary system transformed into a stellar orphanage, drifting on its own terms. Even binary star interactions can play a role. If one star in a binary explodes or collapses, the gravitational configuration shifts dramatically. A previously stable planetary system, orbiting the common center of mass, may suddenly find itself unmoored. Depending on orbital parameters and timing, the system may remain bound to one stellar remnant, split into two separate systems, or be entirely ejected as a whole. These systems may still retain planets orbiting a compact object like a white dwarf or neutron star, but their original identity as a solar system, a coherent set of planets orbiting a luminous star. What happens next depends on velocity, mass, and time. A planetary system ejected from its star may drift through interstellar space for billions of years. If the ejection velocity is high enough, it might even escape the gravitational pull of the galaxy and drift into intergalactic space. The universe becomes its new frame of reference. With no source of illumination, these worlds plunge into cold and darkness. Surface temperatures plummet unless there is a source of internal heat, residual warmth from formation, radioactive decay, or tidal interactions between planets and moons. If the system includes a gas giant with sufficient mass, its gravitational influence may keep smaller bodies in stable orbits for eons. The intriguing part is that life, under very specific conditions, might still be possible in such systems. If a terrestrial planet possesses a thick atmosphere and an insulating layer of ice or gas, it might trap geothermal heat. Subsurface oceans could exist, warmed from below and protected from the bitter cold of space above. Life in these oceans would be fundamentally different from life as we know it, not reliant on sunlight, but on chemical and thermal gradients. On Earth, deep-sea hydrothermal vent ecosystems operate this way, thriving in total darkness. A nomadic planetary system might host similar conditions, entirely isolated ecosystems, oblivious to stars, galaxies, or cosmic history. Detecting such systems is profoundly difficult. They emit little to no light and are faint even in the infrared. However, microlensing surveys, which detect mass by how it bends background starlight, offer a narrow window into their existence. A full planetary system passing in front of a distant star could, in theory, produce a complex microlensing signal with multiple peaks or durations, hinting at the presence of multiple orbiting bodies. Future instruments with higher sensitivity may someday reveal such patterns, offering the first glimpse of planets moving through the dark, bound not to a star but to each other. Galactic nomadism also raises deep questions about the formation and evolution of planetary systems. Are stars necessary for planetary systems to begin with? Could a massive gas clump collapse into a substellar object like a brown dwarf and still gather planets? Some simulations suggest it's possible. Even without stellar ignition, gravity and turbulence can shape disk-like structures around brown dwarfs or massive planets. These disks may form moons or small planet-like bodies, miniature systems that never had a true sun. In such cases, the system isn't ejected. It simply never had a stellar home to begin with. It is born nomadic. The galaxy is likely teeming with such anomalies, not rare but simply invisible to us due to the limits of our detection methods. We detect systems that emit light or perturb their stars. We miss the silent ones. For every Earth-like planet we detect through transit or radial velocity, there may be dozens of silent Earths drifting unseen. Planetary systems without a home challenge the centrality of stars in our cosmic thinking. They remind us that the processes of formation and survival can be far more resilient, far more flexible than our models suggest. In terms of motion, these systems become part of the galactic halo, the spherical region of stars and dark matter surrounding the main disk of the Milky Way. Some may oscillate through the galactic plane, passing near other stars and possibly being captured once again. A rogue system passing close to a star could, in principle, exchange gravitational energy and become recaptured, forming a new hybrid system. The possibilities are countless, but statistically rare. Once cast into the dark, most remain there, and yet they persist. Despite the cold, despite the silence, despite the loss of their central flame. Gravity holds them together, not to a sun, but to each other. Planets continue to orbit, moons continue to rise and fall over cratered landscapes, and geological processes slowly tick forward. They are invisible survivors, reminders that motion does not require illumination, and that complexity can thrive even in the void. From a philosophical perspective, these nomadic systems embody a quiet resilience. They are not tragedies but testaments. Cast out of familiar order, they become something new. Structures born of light that learn to exist in darkness. In them we see echoes of a deeper truth, that belonging, whether planetary or personal, may not always come from orbiting a central source. It may come instead from what remains when the center is gone. What holds together, what endures. And somewhere out there in the long, slow drift between stars, an unseen planet circles a dead core or a hidden giant. It knows no sunrise, no calendar, no constellation to chart its sky, but it moves, faithful to gravity, rich with memory, and that may be enough. And now, my friend, we've wandered through binary dancers, vampire stars, and drifting planets that no longer call any sun their home. All of it, still moving, still held together, even in darkness. If you're still awake, I think you might enjoy another journey, perhaps a quiet exploration of quantum reality, or a visit to the deepest parts of space and time. You'll find a link waiting for you whenever you're ready. But for now, rest well, and may your dreams drift gently among the stars.